Welcome to the second rotation one. You might remember this one because it was on your rotation test. So it says in the diagram above we have a disk, moment of inertia is 1/2 mr squared. It's moving to the right, it's going to drop 1.2 meters vertically, and it is initially moving at 6 meters per second. The disk rolls without slipping, so what that tells us is V equals R omega. And our goal is to determine the velocity of the disk after it rolls down the hill. So let's think about what happens. We have a combination of potential, translational, and rotational energies that will be converted into translation and rotation. I'm going to go ahead and declare along this purple line H equals 0, so your potential energy on the right side of the equation is 0. So let's expand this. mgh plus 1/2 mv squared plus 1/2, we'll call this v initial, 1/2 I omega initial squared equals 1/2 mv final squared plus 1/2 I omega final squared. For the value of I, I'm going to plug in a 1/2 mr squared, and for omega, I'm going to plug in a v over r. I can do the omega substitution because it tells me that this rolls without slipping right here. So, continuing on to expand this equation, mgh plus 1/2 mv naught squared plus 1/2 mr squared. Omega squared, so that will turn into a v naught squared over r squared. That's going to equal a 1/2 mv squared plus 1/2 mr squared, v final squared over r squared. There's some good cancellation I can do. As you remember from the formal lab, the radius does not impact the speed as it rolls down, and neither does the mass. Mass finds its way in all 5 terms. So, takes us to gh plus a 1/2 v naught squared plus a 1/4 v naught squared. That will equal a 1/2 v squared plus 1/4 v squared. Simplify a little bit more. gh plus 3/4 v naught squared equals 3/4 v squared. V will be the square root of 4/3 gh plus v naught squared, all of which is under the square root. So now the last step is, well, what's h? What is v naught? V naught is 6 and h is 1.2. G is obviously 9.81. So coming back here, square root 4/3 9.81 1.2 plus 6 squared equals, grabbing the calculator, square root of 4/3 times 9.81 times 1.2 plus 36. That whole quantity is under a square root, and I get 7.19 meters per second. That is your V final. Now part B says, okay, this is the new shape right here. It's the disk with a hole drilled into it. So we drill a hole into the center of the disk and making it shape more like a donut. Again, given an initial velocity of 6 meters per second, and it's going to go down the hill. Will the velocity of the new object be greater than, less than, or equal to that which it was before? So you may say, well, it lost some mass. How's that impact it? According to this line right here, the loss in mass doesn't make a difference whatsoever. What does change is this and this. The coefficient for the moment of inertia. The coefficient for the moment of inertia is going to increase. So since the coefficient for the moment of inertia will increase, instead of having a 1/4 and a 1/4, you would have something closer to 1/2. Let's say for the sake of an argument, it was actually a complete hoop. So that would make this a 1/2 a 1/2. This will go away. This will go away. This will go away as well. And the result, square root of 9.81 by 1.2 plus 36 will come out to 6.91, which is less. Moral of the story is, as this coefficient increases, more energy is going into rotational motion as opposed to translational motion. And the result is that which has its mass closer to the rotation axis of rotation will end up with a greater velocity.